Hello everyone, this is Phil Sando, and today I'm going to talk about the problems called closest coin, which is also um, one interview question. Um, it looks like it's just very typical problems, but when there's a lot of follow-up and extension for these problems can make these problems interesting and basically just we'll test the interview candidates in a different perspective. All right, so let's directly dive in. If you like these videos, you can support me by subscribing my channel or click likes for the video. In video below, you can find the code of these problems and all of my video list at description. So the problem looks very similar. So we are given a n by n grid. Then we have k coins in different grid cell. Then if we are given starting position, and also we know we can only move up, left, right, down, then what's the closest point we will reach? So here we have a constraint here, say the k is guaranteed to be much smaller than the n square. So I draw a grid to further explain the problem. Here I think the place I plot cross means the start position, and if I plot circle here means that we have coins here. Apparently, these coins is the closest coins we are looking for because it only takes us to move third times, right? So even right, down, down, or down, down, right, we can reach this coin. And for these coins, it take another step, down, 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 right, and for this one. So this one is the coins we are looking for from these problems, and we should return this location. You can pause here to think about how you will solve this problem. All right, so given the hint here, like k is always much smaller than the total length of the grids. Yeah, so we think just why we are just not using exhaustive search algorithms just to iterate all the coins and calculate distance from the starting position. And yeah, here is solution. One thing for this exhaustive search algorithms is like we need to define the cost function. What's the distance will be? So here we can use L1 distance because we only allow to move up, left, right, and down. So that is exactly what's the definition of L1 distance is measure the absolute value of difference between two position x plus absolute difference in y. Here we define the signature of the function as the start position as input and the coins, all the coins positions and the grid length here as well. We're going to return a pair of the closest coin. Then I'm using a main element here to iterate all the coins. Then also define the L1 distance as lambda here. Yeah, it's pretty simple, and eventually we'll return the result. Here I just make sure I have the assumption that we always have the coins in this set. Then let's do some analysis for computation. Of course, big of k because we need to iterate all the coins. We don't allocate extra container, so the space complexity is big of 1. All right, so then let's trickle the condition of these problems a little bit. Say here now k is not much smaller than n squared anymore. For instance, we have k is close to the n squared and can also be equal to n squared. This is the only condition we change for these problems. Then do we have better algorithms to solve these problems? You can pause here to think about that. All right, and the answer is yes. Then this algorithm is BFAs. I'm going to introduce the implementation of BFAs for these problems first. Then I'm going to explain why this one is better than the previous algorithms given the conditional change. If you have viewed my previous videos about the BFAs, I always using the same templates. Then here you also can take this function as a template when you implement the BFAs in a 2D matrix problem. So here I use the help variables or directions to define the movement rules. This up, left, right, down, and have a queue to store all the position I want to visit. Also, I have a visited here is 2D vectors to record whether the current cell is visited or not. So I try to not to visit the already visited position. Otherwise, there is an endless loop later. Same thing to while loop. I got the current positions from the front of queue. If it's visited already, just skip this one. You also can move this into the for loop here, but this just my kind of habit, so you can do another way around. So then we mark this as visited. By the way, this can be used a bool rather than an integer if you want to save extra space. Then we also check whether we have reached the closest point. If we do, then return the close coins directly. Then going to for direction. The good thing to use this director variable is that we don't need to have the if loop to see left, right, up and down. So we can use the for loops to doing all the movement. Then we have the new positions here because we have 5 this direction stuff, so it can be used by x and y alternatively. So this we always use I minus 1 because I always start from 1, and for y I always use the I. So you can learn this very little trick to make your code more precise. Then also check whether the current position is out of the grid cells. If not, I push into queue. Eventually, if I don't find anything, I will return the empty stuff. All right. Right now, everyone is familiar with the ideas for use BFAs for this problem. Then why it could be better than the exhaustive search before? When we look in the computation complexity, so the worst case of BFS is big of n square. Basically, you can think, but there's only one coin, and maybe it's in the corner of the grid cells. But unfortunately, our starting position is in another corner, so it's take n square. Unfortunately, in worst case. Also, we know k can be very close to n square, so it's also close to big of k. But you may have the answer, right? Why this share the same complexity with the exhaustive search algorithms, but why this one is better? Because here we only talk about the worst case. In average case, which means you maybe got lucky, or in normal case, your complexity can be less than the big of k. But in the exhaustive search algorithms, it's always has to be big of k. And the space here, because we allocate some containers, so for visited, we have to use big of n square to fit for the visited container. But we are assuming the space is not the main decision factor to design the algorithms. All right, so at this step we still haven't done. because we have another variant of the problems. Okay, right now, so if I just don't give this information to you, I I'm not telling you whether k is large or small, or how it's relationship with the n, then how you will approach these problems properly. You can take a pause here and think about that. All right. So yeah, and at this point, at this question is the I think is the most fun part because it kind of interviewer can test um the candidates in a kind of unnormal mindset. Is like how you select algorithms based on some condition. So in the real applications, we used to have a few options of algorithms to solve problems, but maybe this is not optimal one always uh, optimal in every case. So basically, what we're doing this, we are just based on some criteria to select a proper algorithms, and this problem is a good example. So right now we know we already implement the BFA search algorithms and the exhaustive search algorithms, but they are not always optimal in every case. For example, um, if k is very small, so definitely exhaustive search algorithms is better than BFA search because BFA search algorithms complexity really depends on the how is the coin distribution. If the closest point is very far away from your start position, it's take a lot of steps to reach that coins, right? But for exhaustive search, you only based on how many coins uh, you have these problems. So it's really done tying to the distance between the starting position and the closest coin. Um, then here we know exhaustive search closest algorithms is k, right? Then what's the BF search algorithms? So remember, condition here, I'm not talking about the worst case. I'm trying to explain based on the average case. Because for the BF search worst case is also big of k. We cannot tell the difference if you're using the worst one. Then for the average, it's still um, difficult to get a absolutely correct estimation. Based on I'm exploring the few comments from the other people's, it looks like the user n squared divided by k is kind of more intuitive way to estimate that. For example, if we think n the total sales can be 4 times greater than the number of coins, so basically you can think you will do like up, left, right, down movement, right? So then in these four directions, you will guarantee to reach the closest point by one shot. Uh, Not by one shot, I mean like if you search one up, left, right, down, you can guarantee to find the one coin if the coin can be assumed to be distributed evenly based on your search trajectory. Right, hopefully that explain how we understand this n squared divided by k. But I also understand that this is not the mathematically correct way to estimate. Um, but if you see this problem in the interview, I think how these kind of conditions are being made may not be that important if it's a really precise one or not. I think the more important way is like to show to the interviewer you have this kind of mindset based on some criteria to select different algorithms rather than just stick to one algorithm in every case. I think to solve this problem, another bonus point you just mentioned um, to think of the user KT tree algorithms, for instance. if we would repeat the operations from multiple start positions, um, at this particular condition, use KD tree is the more optimal one. The reason that the KD trees have less computation complexity for each operation. However, KD tree also requires an initialization step, which take us extra time. So if we only do this operation once, I think it's not worth to do the initialization or have allocate some space to store the initialization result. But if we repeat the multiple operations, it's definitely worth it because it's greatly reduced the computation times for each operation. So if I make videos to explain the KD tree later, I'm definitely to link that videos into this page as well. All right, so I think that's how I think to approach this problem. But definitely, I think for this n squared divided by k here, it's definitely further discussion whether there's better options. If you have a good ideas, please feel free to drop the comments below the videos. All right, so that's all. See you in next video.